Welcome, everyone. Thank you for attending today's SEL webinar. Before we get started, I'd like to bring a few items to your attention. This is an audio-only broadcast. All participants have been muted. If you have any questions throughout the presentation, please use the Q&A tool at the bottom right-hand corner. Our live technical staff will address your questions in a private chat throughout the presentation. Please submit your questions to all panelists. Any questions that are not addressed during this live event will be answered by our experts via email. Our presenter today is Scott Winke. Scott received his BS degree in electrical engineering with a power emphasis from Washington State University. Prior to joining SEL in 2013, Scott worked at Itron. At SEL, he's a product manager in the Power Systems Group of R&D and is responsible for transmission and substation product lines. He has been a member of IEEE since 2012. Our panelists today are Erin, Menadave, and Trevor. Erin Jessup received her BS and Master's in Electrical Engineering with an emphasis in power from the University of Idaho. At SEL, Erin is an engineering manager in the R&D Protection Systems Group and has supported the TiDL development team. She has been an IEEE member since 2012. Menadave Rajasekharan received his BS from the University of Madras, India, and Master's in Electrical Engineering from the University of Idaho. At SEL, Menadave is a senior engineering manager in the R&D Protection Systems Group and has led the Sampled Values development team. Trevor Matson received his BS in Electrical Engineering with an emphasis in power systems from Washington State University and is pursuing his master's with the same emphasis at the University of Idaho. At SEL, Trevor is a product engineer in the R&D Protection Systems Group and supports the SEL 487E and SEL 487B. In today's webinar, Scott will examine a new point-to-point digital substation solution that was designed with simplicity in mind, time domain link technology. I will pass the microphone to Scott.
Thank you. So one thing before we get started, like it was mentioned, we'll answer questions through chat. We have a couple points in the presentation that we will break to answer questions in the middle. So as you have questions, just submit them. And if we don't get to your question, like it was said, we will get to it through an email later. So don't wait until the end. Go ahead and submit them as soon as you have them. So today what we're going to discuss is, first we'll just kind of talk about a digital substation implementation. And what we mean by a digital substation is the idea of replacing analog connections with digital links, and particularly replacing analog signals such as CTs and PTs with a digital signal so that we can combine all this data into a single link. First, we'll kind of go through some topologies to just reduce substation wiring. So these are not full digital substation implementations, but also things to consider when you're looking at these technologies. And then we'll kind of get into two newer solutions. First is the IEC 61850-9-2 standard. So this is also referred to as sampled values or process bus. In this presentation, we will refer to it as sampled values. And then also the time domain link technology or TiDL technology. This is a point-to-point simplified architecture, and we'll get into what that entails later in the presentation. So the first thing is, why would you want to implement a digital substation? One of the major drivers is improved safety. Because we are removing these high-energy CT-PT signals from the control house, we can generally improve our safety because these are not where people are typically working. We can keep them out in the yard so we don't have to worry about things like open CTs in the control house. Another benefit is situational awareness. All of these digital links are generally going to be self-monitoring, and so as opposed to a simple copper connector, we can know exactly when the link is damaged or degrading and can alarm to hopefully take mitigating action before it becomes a critical failure. And then another big benefit could be reduced cost. Obviously, if we remove a lot of copper connectors with a single fiber optic cable, there's a lot of material savings there. There can also be savings in the number of terminations in the field, so we can see some labor savings. The amount saved is obviously going to vary depending on your installation and would have to be kind of a case-by-case evaluation, but you can see significantly reduced costs. So in the next slides, we're going to have kind of a simplified architecture, and just to kind of make sure we're all on the same page, in the upper left, that symbol is for a traditional communications and control building. So this is a control house that's going to house all of your relays and other equipment. In the upper right, it's generally going to be something similar. We call it a kiosk because with many of these digital substation technologies, we can downsize our control house because we don't have to have as much equipment. We also call out the battery kiosk there because in our architecture, we're going to be running power from that centralized location out into the field. In the lower left, we have our field cabinets. So the one on the left is symbolizing, a just simple cabinet with nothing inside necessarily. So that's more in the non-digital substation implementations. And then the one on the right, we will put a blue box inside if we're specifically calling out an IED or other device inside the cabinet. In the diagrams, we don't have details of what the connections are, so any copper connection is going to be referred to as a wire, and anything that's a fiber optic connection will be referred to as a cable. So if it says wire, it's a copper hardwired connection, and cables are fibers. So first, let's just kind of do a quick overview of what a traditional approach might look like. In an example system, we essentially wire everything from the equipment all the way to the relay. Along the way, we would generally put it into some kind of marshalling cabinet in the yard, and then have a trench where we send all that wire to the control house, where we wire it into a test block or a test switch, and then to the relay. So with that, in our example, we have 44 hard wires. And so from an architectural standpoint, it would look something like this, where we have all the connections, we bring them to a cabinet, and then run it all back to a centralized control house. So one way to reduce the amount of wiring is essentially to distribute that control house. So one possible way to reduce the wiring is to essentially put the relays out into the yard and just have each relay communicating and protecting locally. So in this case, we can just cut out all of the wiring from the yard to the control house. This is similar to an approach we'll talk about later, with one key difference that we'll touch on when we get to that. Another way that we can reduce the amount of wiring is using a hybrid system where we still hardwire our analog signals, but we can use an I/O module out in the yard so that we can consolidate all of our I/O signals into a single fiber optic connection. And so using that same example, what we do here is we essentially can segregate our I/O and our analogs. The analogs still get hardwired back into the control house, much like you would in a traditional setup, but we have the relay communicating with an I/O transceiver out in the yard through a fiber optic cable. And so what that would look like architecturally with our example is we would still have that white hardwired connection from the cabinet all the way back to the control house because we still have our analog signals. But now we're also running generally in the same trench. You would have a fiber optic cable for communications purposes to transmit our I/O signals to that transceiver. So the main focus of this presentation is to talk about this topology where we essentially have everything communicated over a digital signal. And so for these solutions, what we do is we wire everything in the yard to either a relay or a merging unit, which is the MU there. We'll touch on what exactly a merging unit is later on, but essentially all of the hard wires are out in the yard, and then that device will communicate through a fiber optic cable back to the control house. If it's a networked solution, then it would be into a switch, or if it's a point-to-point solution, it would generally be to a processor on the relay. So in this topology, essentially, we would have our device out in a cabinet in the yard, and the only connection we have back to a centralized location would be for communications and power out to the units in the field. So in that way, we can eliminate a lot of the wiring that is just all going back to that central location. So next, we're going to talk about the solutions available today, but first, I think this will be the first break to answer any questions if we have some. So the first question is, do we still need the high voltage equipment? I'm assuming, the high voltage equipment, you would still need it out in the yard, but the idea is you would not need it in the control house where people are generally going to be working. Okay, the second question is, can we explain the switch function or photo? We'll get into that a little bit, but essentially with some of these new technologies, there is because there's a digital communications link, you would run it into a switch, and so all of your protection signals would run over a switched network. We have some slides later on that kind of show what that topology may look like, but obviously it's going to vary depending on what your standards are, what your application is. So I think let's just keep moving on then, and we'll get to the other questions later on. We have a block of time at the end just for Q&A. So we're going to talk about three solutions that can be used to implement this digital substation concept to varying degrees. The first we'll talk about is just putting the relays in the yard, which is similar to what we mentioned earlier. The key difference is we include a communications link back to a central location. We'll talk about this 9-2 sample value solution, specifically the light edition or 9-2 LE guideline from UCA that's used by most manufacturers to make an interoperable solution. And then last, we'll finish up with time domain link or TiDL technology, which is a new, fast, easy to install and simplified solution. So the first one we always like to talk about is just to simply move the relays out into the yard. You can put them near to the equipment, and you just run all of your connections to that device and then have a communications link back to the control house so that we can collect SCADA data or any other communications with the relay that we need. And you can use DNP protocol, 61850 protocol, whatever is built into the relay. We like to mention this because this is a solution that we've been using for years. Because relays are designed to be in harsh environments, with SEL specifically, we have a temperature rating of -40 to +85. We have customers in very harsh environments that have been using this solution. There's a case study on the website you can reference of a customer in Vietnam who's done this, and then we also have customers in Brazil that we have a video of next to show their experience with this solution.
E a parceria vem trazendo frutos positivos aí a nível de supervisão, controle e monitoramento, modelização das subestações. Electro was using BMP3 protocol, which like other SCADA protocols only do 3 of the necessary 18 power system applications. They wanted to modernize and use 62850 to provide much more functionality. 62850 provides 10 of the 18 power system applications. And then the SEL methods and the relays provide the remaining 8 missing applications to make the electron network complete using protocols like FTP and Telnet. Com a implantação da norma 6150, a gente consegue muitos ganhos na questão de manutenção do sistema, aumento da periodicidade de manutenção nas subestações, a confiabilidade frente aos equipamentos que nós estamos instalando, The fact that SEL makes relays and Ethernet interfaces very rugged means we can move both out into the yard. And then we can move the information from the substation yard to the control building over a fiber optic cable using digital messages instead of bundles and bundles of copper conductors. A redução da implantação de cabos na subestação, mais que 30% dos cabos são eliminados. Eu tenho ganhos para a parte de acesso e também toda a parte de controle e monitoração online. Análise de projetos, assim como o projeto, é muito simplificado. Redução no tempo de comissionamento, supervisão e controle à distância com possibilidade de alteração nas lógicas e ajustes dos equipamentos. SEL has been providing the protocols within the 62850 standard inside our relays for over 10 years. SEL methods, SCADA methods, and IEC 62850 methods all coexist in SEL relays, and the customer is free to choose one or all of them. Os grandes benefícios que eu posso citar frente à modernização sendo feita na Electro é a segurança dos nossos eletricistas, onde não há mais a necessidade de estar indo até a subestação para fazer qualquer ação de manobra, de conexão, e isso a gente consegue fazer via remota. Pondo menos ao risco, assim como garantindo uma maior confiabilidade da energia entregue aos nossos clientes. Desde o início do trabalho junto à Schweitzer, é importante destacar que a gente sempre teve um pronto atendimento, mesmo em situações emergenciais. O suporte técnico apresentado pela equipe da Schweitzer do Brasil é, na minha maneira de pensar, incrível. Então, são pessoas que nos disponibilizam e estão sempre tentando nos dar a resposta o mais rápido possível. É um processo bem positivo, que vem nos atendendo adequadamente e resolvendo os problemas dentro dos tempos adequados e necessários para a nossa empresa.
Okay, so that's just an example of a customer that has implemented this in their substations and has had a lot of success with it. But now we'll move into the newer approaches. The first one we'll talk about is sampled values. So this is a networked solution, which we have some diagrams later. But it complies with the IEC 62850-9-2 standard, like we mentioned before, using that UCA guideline. For these solutions, we want the devices out in the yard to be able to survive those harsh conditions, so it's based, at least for SEL, on the 400 series hardware. The other thing to consider is that because we now have a non-deterministic Ethernet network, we do have to time align all of our data, and so how we do that is by getting time to every unit in the system. With our implementation, we either use an IRIG signal or precision time protocol, which is described in IEEE 1588. It's essentially a way to get high accuracy time through Ethernet connections. So I've used the term merging unit a little bit before, but just for some clarity, what exactly are we merging? The idea is we're merging both current, voltage signals, I/O, discrete status is what it's on this slide, as well as a clock input. So like I said, we need some kind of way to align our data. And then all of that is combined into a single unit and then sent out through a digital communication link. So the merging unit in the slides, in the next couple slides, is what would be out in the substation yard. So just a very simplified architecture of that. We generally are going to have two Ethernet networks. So the main one that's new is this process bus in the middle. And so what this is it's connecting the merging units in the yard. So on the bottom, we have all of our merging units to all of our relays, which generally would be inside a centralized control house. This is all of our protection data, and so we use two different protocols to transmit our data. The sampled values protocol in 9-2 transmits our analog signals, so our CT and PT signals, and then Goose is used to transmit digital data or discrete data. The other network is generally what you would think of when you're thinking of Ethernet traffic in a substation today, and that's station bus. So this is for anything that is non-protection critical. So you can still have goose messages, just like you're using today, but you would also have all of your IP traffic, possibly MMS, DNP. In this particular example, we're showing PTP synchronization through the station bus, and that's why we have the 2488 clock on the diagram here. It could also be run through process bus, but in this particular example, that's what we're showing. It is worth noting that this is a very simplified example of what a network would look like. In reality, that single switch is probably a network of switches, which may look something more like this. So what we show here is we have a switch out in the yard for each merging unit and a switch for each relay with many connections spanning between the two. So the reason for this is that to mitigate any sort of failure points, what we can do is we can use technologies like spanning tree protocol or software-defined networking to reroute traffic in the case of a failed link. So for instance, if my primary link between the merging unit and the relay on the left is severed, like in the slide, if I lose that, now that primary link is severed, but what I can do is I can use the other available paths to reroute the data so that I can recover from that. This can be very appealing, especially with something like software-defined networking where our failover times are very fast so that we don't interrupt protection, essentially. But this does come at the cost of complexity because now we have to use things like VLANs or flow controls to make sure that our data is getting where it needs to go and we aren't flooding all of the relays with all of the data, even the stuff it doesn't need. So there are challenges associated with 9-2. Again, because we are now introducing an Ethernet network to our protection critical functions, we have to very carefully engineer that network. We need to use tools like VLANs and priorities and flow controls to make sure that the data is getting where it needs to go and our network is operating the way that we want it to. The other thing is now we have to send time out to all of our merging units in the field, where typically we have an Ethernet clock in the control house, or not Ethernet clock, a GPS clock in the control house to synchronize all of our relays. We now have to send that signal out to all of the units in the yard or put a clock out in the yard with each unit. It's just another consideration. The other consequence of putting these units out in the yard is they are programmable. We have to be able to tell them how to address their packets to make sure they get where they need to go. And so that can create some cybersecurity concerns, especially with regulations such as NERC-CIP. We need to make sure that it is physically secured as well as cyber secured. The other one is that the 9-2 LE guideline generally creates interoperable solutions, and from testing that we've seen, it is indeed the case that it's interoperable. It's not as simple as plugging vendor A and vendor B together, but we can get there, but there's no guarantee that that the solution is interoperable just because the LE guideline was created, but it's not strictly enforced to be compliant with the standard. So before we move into TiDL, I think we'll answer a couple more questions. So, Erin?
Yeah, so a couple questions that have come up are, do you need to run power to the relay or the devices in the yard? And yes, in all of these cases, you do need to power the device that is measuring the analog and digital information in the yard.
Yeah, so that can either be running it from a centralized source like we showed, or you could have batteries in each kiosk to power the device.
Another kind of general question is, are these technologies being applied in real projects? And the answer to all that is yes.
Yes.
And it goes on to talk about redundancy, and you know what I've found with redundancy is that different utilities have different standards on how they do redundancy. And so these solutions are flexible to meet a variety of those standards.
Yes. Yep. We can add in more clocks if we're worried about losing GPS signal, use terrestrial time sources, things like that. These are all, again, just considerations. We mentioned these as challenges, and we're not going to say that these challenges can't be overcome. It's just these are additional things to consider when you're looking at this solution. And the reason we bring these up is to kind of get into why we went and implemented TiDL the way we did, because TiDL can help address some of these challenges that we pointed out in the networked solutions. So from the cybersecurity standpoint, because we have a point-to-point architecture, there's less access points to this protection data, and so because there's no switches, we can be more, or it's easier to become cyber secure. The other point of that is that the node out in the field, which we'll get to in just a second, is non-programmable. It's a non-routable protocol that we use in TiDL. 9-2 in theory should also be implemented in a non-routable fashion, but because we're going through a switched network, we can use techniques like tunneling and become routable without too much deviation from the standard. Again, not the recommended way to implement it, but people will do what they need to do. Another nice part about TiDL is we solve the time synchronization problem. There's a built-in methodology to synchronize all of your field devices. Fewer devices, what we really mean by that is that there's fewer possible points of failure because we just have relays and field modules. We don't have switches, we don't have clocks. It becomes easier to manage those points of failures and sort of plan for those points of failures. There's also some nice commissioning and troubleshooting features that we will talk about, and no network engineering is required for the troubleshooting or any of that. So now that we've said all these things, what exactly is TiDL? Well, what it is a 400 series relay. So in the slide, what we're showing is a 421, and it's connected through a point-to-point fiber to the 2240 Axion. So this is a modular platform that we've used for many years now. It makes it a very flexible solution where we can essentially add or subtract modules to fit the application. We'll get into what those would look like here in a couple slides. So one other nice thing we like to bring up is we use the IEC 61158 EtherCAT protocol in TiDL. And we can use that single protocol for both our current and voltage data as well as our I/O. So in the 9-2, we're using two separate protocols that we need to program, essentially, with sample values and goose. But in this, we can combine them all onto a single link with a single protocol. So what is EtherCAT exactly? It is Ethernet-based field bus technology, and so what we mean by that is the physical connections are still the same as an Ethernet connection. It is a multi-mode fiber connection, but if we were to put it into an Ethernet switch, it would not recognize it as Ethernet. Like I said, it's in IEC 61158, and it was originally built for industrial I/O expansion, and so it's a very scalable and distributed application, but most importantly, from a protection perspective, it is very deterministic. It's also been used in our Axion platform since 2011 when it was introduced. We mentioned that just to kind of point out that it's a protocol that we're very familiar with. The Axion has been using it successfully in mission-critical applications since it was introduced in 2011, and so we felt pretty comfortable in applying this to the protection world. Like I had said, we essentially don't rely on time for protection. The relay can keep all of our nodes synchronized so that they're sampling at the same time. so we don't have to have a time signal out to the field node. This is all done automatically by the relay. There's no configuration on the user's part to set up this time synchronization. With that being said, the relay does still have a time signal on it, so you can still connect it to time, and that's generally best practice for wide area analysis is you want to have a time signal to your relay, but if you were to lose your time signal, your protection still can remain up and running irregardless of that signal being present. So the question is, all right, if there's no network engineering and all of that, well, how does my relay map all of my currents and voltages? Well, how we do that is you can see on the right, there's a picture of the back of what a TiDL relay looks like. And so what we did is we replaced the CT and PT connections with these fiber optic ports. So these are EtherCAT ports, and there's a total of 8, so we can communicate with up to 8 Axion units. We don't always communicate with 8, but essentially how we plug in our Axions to those 8 ports tells our relay how to map the analog values. So the trade-off with that is they are predefined topologies, so you have to connect them a certain way, and they're fixed. We generally try and kind of look at 2 aspects when we were defining these topologies. We want to look at copper reduction and device cost. So what we mean by that is copper reduction is saying I can reduce the amount of copper I have to run around my substation by putting the device close to where it needs to be. But the flip side of that is I would have to buy more devices, so there's also topologies we created to address that, where we essentially have fewer devices with the trade-off of having to run more connections to those devices. In a couple slides, we have some example topologies just to kind of show what we mean by this point. So if we look at those connections there, we mentioned in a few slides ago how TiDL is easy to commission and troubleshoot. One of the ways we do that is with this commissioning button on the left of the EtherCAT board you see there. So essentially when we pull the relay out of a box and we get it new, it will not talk to any of the Axion units. So what we can do is we push that commissioning button. The relay is going to go out and talk to the Axions and figure out what it's connected to. And then if it is a valid topology, it will turn the LEDs green, indicating that everything is good to go. It will also indicate which ports are commissioned. Like I said, so this is confirming both the analogs in our topology, but it also validates that we have our I/O correct, just that we have the correct number of I/O cards. The other nice thing about this system is the relay will remember the last commissioned state through a power cycle. So once I have commissioned the relay, it won't forget the Axions that it's associated with until we do a predefined set of actions, which is beyond the scope of this, but if you look in your instruction manual for any relay that you're trying to use, it'll explain how to do that. But the idea with this is I can test a relay and Axions on, let's say, a test bench. I can have them associated, and then when I move it to the actual field installation, the relay will remember how it was commissioned, and as long as I connect everything exactly like I did at my test bench in a controlled environment, the relay will just enable. If I miss any of my connections, then the relay has ways of signaling that with the LEDs. So we can know which port is the problem and figure out, and we know that the problem has to be between that connection on the relay and the connection on the Axion.
Scott, so we have a question that kind of goes along with this. It says, what happens when a connection is lost between any device and like a broken fiber or some other thing like that? So in a TiDL system, if we lose an Axion, the device will disable and send an alarm contact. Only if there's CTs.
If this, correct, sorry. If we lose an analog signal, it will do that. If we lose the digital I/O, it asserts a relay word bit, but the relay itself will not disable. So that's kind of up to the user to make sure that you design your system to alarm when you lose it so that you know exactly what's going on. So the topologies that I had talked about earlier, here's a couple of examples to kind of show the points that we were talking about, copper reduction versus device cost. So this would be, for instance, a topology for copper reduction. So this is one example from the 421. So this is a breaker and a half kind of scheme, and we have 5 Axion devices. So we have to use a lot of Axions, but the trade-off of that is I can put them right next to the device that I'm actually measuring. So if this was a very large, physically large substation, and all these CTs and PTs are located far apart, I can instead just run a one fiber connection instead of having to run all my copper to a centralized location. And then all of those fibers go back to the relay and connect into the different ports on the relay. And the flip side of that is here's a topology that reduces the device count. So in this case, we have the same analog signals, so we still have all the same number, but this time we're running them all to a single Axion node. So we have to have a couple of CT-PT cards, which we're showing here, but the nice thing is I only have to buy one Axion with the understanding that I now have to run copper connections to that single Axion. So some of the other benefits of TiDL is with consistency. To talk about the proven Axion technology, the idea with this is we introduced the Axion in 2011. We've used it in harsh environments and critical applications, and so we know it's a very reliable platform, and it also brings us some nice modularity. And so we can leverage that and use that proven technology to make our application flexible and still work anywhere and be reliable. From the relay side, essentially the relays are unchanged. So the protection settings are the same today as what you would have in a hardwired relay, and they're still running the same algorithms, and so we can apply the same schemes. Essentially, we just have to change how we're getting our wiring, but from a settings and protection scheme standpoint, nothing should change. With the sample values solutions, generally those are engineered to try and be very similar to what people are using today, but we do have to introduce some new settings just to address the networking aspect of it. So this is kind of just the wrap-up of what we were talking about. We show a lot of things that we think TiDL has a very strong posture in. Cybersecurity, it's much easier because the Axion is non-programmable. We say easy because we're not saying that sample values cannot be cyber secure, just that we have to take extra precautions because it is a programmable device out in the yard. By using the point-to-point architecture, we can simplify things like network engineering. And also with the built-in time synchronization, TiDL is independent of an external time source for its protection. And like the last slide mentioned, the settings are the same as they are today. That's not to say that sample values does not have some advantages. The flexibility in networking is a big one. I showed that one example, and while it does take extra complexity to engineer failover paths, it does help mitigate some of these concerns about points of failure where it can have redundant switches, redundant clocks, and all of that, with knowing that the trade-off is I have to engineer those paths, I have to account for all of this data, and make sure that I am being responsible in where my data is going and how it's being delivered. The other one is that it is interoperable. If that is something that is a big concern, we've seen in installations that, or in test installations, that 9-2 LE is interoperable between manufacturers. It's not as simple as plugging manufacturer A and B together, like I mentioned, but it is possible with enough effort and some work to make that happen. So that was all I have for slides. At this point, I think we can take some questions and have any kind of discussion if you guys want.
Great. Scott, I did want to comment on one question that a few people have asked. It's asking about how many relays can one Axion module talk to. So in the initial release, it's a point-to-point connection, so one Axion to one relay. However, in a future release, it will be one Axion to multiple relays.
Yep. So there's also a couple of questions along the same line of, what is the added delay due to these technologies, the impact to, your tripping time. So in both cases, both in sample values technology and in TiDL technology, yes, there is an additional delay. In the TiDL technology, it is fixed at 1.5 millisecond communication channel delay. In sample values technology, there are other varying factors, especially when you're using different vendors, merging units along with SEL relays. So it's kind of a programmable thing, and it's based on your network design. So the minimum is 1.5 millisecond, but it could go up to 3 milliseconds, based on how many devices are connected to the network and how the network has been designed. Yeah, that's kind of one of the challenges with the network design is it's a non-deterministic network. That's just the way Ethernet is because it was never designed it was not built with protection in mind. And so that's one of the things. It depends how many switches you go through and things like that. Each one adds a little bit of latency. So there's also a question regarding interoperability with third-party devices. So with the sample value technology, because it's based on a IEC standard, SEL relays and merging units will interoperate with other vendor devices who also conform to the standard. In the TiDL technology, it's a proprietary solution. If there's any other questions, just type them in. And if some of these questions, if we're not answering right now, it maybe requires quite a bit of explanation, and so we'll probably end up doing an email response. So it's not to say that we're trying to ignore anyone, it's just sometimes an answer may take more than a 1-minute explanation. Yeah. So it looks like there was some questions along the lines of how do we test these solutions? That's going to kind of depend on your method, your standards of testing. Essentially what it boils down to is that you'd have to do some injection out in the yard. You're going to have to do that just to check the A to D and your wiring connections. For the actual field installation. However, there are tools and ways to help out with that. But as far as testing the protection algorithms with the TiDL technology, because that commissioning process makes the relay remember all of your connections, our recommendation is that you thoroughly test your connections or test your relaying on a bench or in a test setting. And then know that because the relay will actually remember down to the serial number of the Axion that it's connected exactly the same as when you were testing it in the lab. And so you would still, again, just have to check your connections once you're out there, but you should be thoroughly testing it in the lab. Yeah, and the way you would check your connections is generally through a metering command. So similar to what you're doing today, just to verify polarity and things like that. Sampled values, there are some tools that people have to essentially inject faked signals so that we can manipulate them at will. This can be used to test protection algorithms, either in a test bench. It could also be used in the field, but in general, once you've tested your protection, the algorithms are not going to change once you program the device. So it's not as critical to test out in the field. Either way, for maintenance purposes, just to verify that the electronics are still good in your emerging unit or Axion, you're still going to have to inject out in the yard. It looks like, okay, so Aaron's saying there's a question about, are there any settings for the Axion in TiDL? The answer to that is no. Basically, there's nothing to set in the Axion. The only way it'll do anything is by talking to the relay. The only possible setting is you can change it from a 1 amp to a 5 amp through a command in the relay. So it's 1 amp, 5 amp software selectable, which could be a setting depending on how you want to look at it, but it's a command.
So another question, can the TiDL relay have the 61850 option?
The answer is yes. So we talked about process bus and station bus. So the TiDL portion of this is really only replacing that station, or the process bus, excuse me. So it still has Ethernet, and it can still talk 61850, can do MMS and Goose to other relays. It's just the data acquisition portion that is using this EtherCAT protocol.
And just to clarify, as a merging unit functionality, the Axion or the TiDL technology does not support the 61850 9-2 option.
Yep.
So for that, there are two separate devices. SEL has a 401 device and a SEL 421 device that can both publish sample value messages as compliant with the 61850 9-2.
Yep.
Yeah, so one of these questions actually makes a really good point. So since the Axion has no programming, is it fair to characterize it as simply a method of a simple method of topology architecture, i.e. nothing else changes with respect to the relays, comms, RTEC programming, etc. I think that's one of the really the key benefits of TiDL is all of your settings that you're used to using today are exactly the same in the TiDL relay. So
correct.
Nothing else changes. There's no network configuration, no Axion configuration, anything like that.
And one other point I kind of forgot to mention is the Axion is the same Axion used today, with the exception of we do not use the RTAC module, so there is no programmable part in the relay. For the Axion in use today, there's an RTAC module that handles all of the data processing locally and then can send it off. But in this one, all of the processing is done on the relay. So the Axion is really just a passive device, more or less.
So another question was, so in the TiDL technology, can an engineer have access to the raw EtherCAT data? And the answer is yes. You could connect to any network switch and then use something like Wireshark to be able to look at the data.
Yes, but so that's more in a test setting. If you're talking about getting the raw EtherCAT data in a field installation, no. You would have the raw data from the relay like you would today. So you can still get your 8 kilohertz ComTrade file to see, the raw data that the relay is seeing, but we don't make the EtherCAT data itself available to you. So you can see what the relay sees. So there's a question, does TiDL also support PRP and HSR? So again, the EtherCAT link is point-to-point, and so that does not have PRP and HSR, but on the station bus side, the TiDL relays do have the option for PRP. So you have 2 Ethernet ports that can run in PRP fashion for station bus purposes. Another question, is it possible to use dual fiber cables to a single relay for redundancy? For sampled values, yes, to an extent. Because the relay is generally only using a single active port, it does have failover, but you can run a failover port for that. With the TiDL relays, no, it's a point-to-point connection today. Essentially, the idea is we want to eliminate any sort of network engineering or complexity, so it is just a single fiber port. But and I know that does raise concerns about points of failure. What we usually try and stress with that is we're still going to use a lot of the same principles today. So basically, we want to have completely separate A and B or primary backup systems. So really, we should be running independent systems irregardless, and so our redundancy is built in through the application, not necessarily the communications path. And that's true for both solutions. So someone's asking, we knew this one would come up, the value of savings in, they specifically say North America. The answer is the answer to every power system question of it depends. We have some case studies, like I'd mentioned, the Vietnam one where they put the relays out in the yard, they saw, I believe it's like 77% savings. Now realistically, I don't think that's going to be everyone's. We had a customer do a pilot and they were expecting about 20%. The only answer is it depends. If you have a specific application that you'd like to look at and get more info on, please contact your local SEL representative and we can kind of work through exactly what it would take to implement either of these systems and sort of get an idea of what the savings would be. So someone asked, is there protection to keep a broadcast storm on the station bus from affecting the EtherCAT network? The answer is they're completely independent. So anything that happens on the station bus is not going to affect anything on the EtherCAT network. Someone asked, are there plans to pass I/O between relays via TiDL? That one's, the short answer is no. The long answer is kind of. So if you look back at this presentation and you go rewatch, the back of the TiDL relay actually does have an I/O board. So we can pass I/O through locally through a hardwired I/O. The other method is you could use something like a goose message on station bus to pass I/O information between relays. So as far as sharing between an Axion and multiple relays, that's kind of tied into that future release that Aaron had talked about. Someone, go ahead.
So someone had asked for 62850 version. So currently the released products are the version 1, edition 1 compliant, and you know, fairly soon, you know, we will be releasing our edition 2 on all our products.
Yep. And the sampled values products are all edition 2 right now.
Correct.
So I think for the sake of time, we'll do just one more question. If you have them, please just put them in anyway. We can get back to you through email, but just for the sake of time, we'll do one more.
So what's the maximum allowed distance from Axion to the relay?
So the maximum distance is 2 kilometers. So you can do 2 kilometers between a relay and an Axion node. So I think that's all the time we have for right now. If you have any last-minute questions, just throw them in the chat, and we'll get to you through an email response later on. All right. Well, thank you for attending, everyone. If you have any other questions, put them in the chat, or feel free to follow up with your local SEL representative, your application engineer, or sales representative, and they can either answer for you or direct you to the right person. So, thank you.
Well, thank you for everyone that has joined us today. We hope you had a great time just learning more about the TiDL technology. If you have any more questions, please let us know. We will follow up with your emails and with all your questions. And a recording will be available within 24 hours on our website under www.sellink.com, Events on Demand Webinars. Have a great week, everyone, and take care. Bye-bye.